Well, hello again everybody, and as you can see we've got on the bench today a piece of test equipment. Well, I actually thought it's been some time since we've had a look at any test gear on the channel. I was actually really grateful when our friend George Christopher actually donated this piece of equipment to the channel. So thank you very much, George. So what we've got on the bench today is what I think is a very unusual and a very interesting piece of test equipment, and it's made by the Dymar Electronics Company Limited, and it was actually built in Watford, England, so that's good, something manufactured in England, which is nice to see. Now I can also see there's actually a little bit of a label which is kind of ripped off here. We can only see half of it, but I can see the second half of the word Storno, so I think everybody will be familiar with the word Storno to do with, well, they used to make business radios, I think, didn't they? Repeaters and power amplifiers and stuff in the business radio world. So this was obviously maybe used in one of their companies, because it does actually say service department. So I think that's interesting. Now, as I said earlier, these really are quite a specialist piece of equipment, but a very useful one nonetheless. And these are actually used for the alignment of SSB transmitters. So they're used for aligning single sideband transmitters. So really, again, quite unusual. So of course we always turn her over and have a quick look at the bottom, and we can just see that there's a fuse holder at this side. There's some kind of a knob, which I'm guessing was probably to wrap the mains flex round. So I'm guessing that's what that did. Maybe the other one's broken off. We've also got something that says meter unit, and this is a Dymar label, so this is telling us what it is. I think it says something like, it's very hard to read. It might be type 70A. Can't really read it. Type 70A, serial number, I think it's 872, so obviously probably a relatively low volume production type of thing this. As I say, it's quite specialist. So we just turn it round again and take a look from the top. Well, it's got a carrying handle on it, but you wouldn't want to carry it very far. It's actually surprisingly heavy. Now, generally speaking, there's not too much going on inside these things, or there shouldn't be, because actually all we've got is two audio oscillators and then a very simple mixer circuit to actually mix those two audio oscillators together and produce an output. And then you would take that output and you would feed it into the microphone input of a transceiver. So I think before we go any further, let's take the cover off and have a look inside. Well, I'm not sure regarding the date of manufacture of this thing, so I'm not sure if it's got valves or transistors in it. Guessing by the weight, I could say this could be a valve device, because it feels like it's got a hefty transformer in at this side. But I don't know, is it going to be valves or is it going to be transistors? Your guess is as good as mine. Go on, take a guess. Now, unfortunately, I haven't managed to find any service information for this myself, because, as I said, it's probably quite an unusual piece of equipment. It's not like a valve radio where they would actually have made many thousands of these on a production line. I suspect probably the whole manufacturing volume of these was, probably limited to a few hundred. So, yeah, who knows whether or not they ever bothered to provide a service manual for it. Right, is that all the screws out? I think it might be. I've got a feeling that this top might lift off now. Oh, so just taking a look inside, it looks like we've got a little bit of a mutant hybrid situation going on. So we've got what I would say is just a valve power supply. That looks a bit bulgy, doesn't it? I can definitely see a bulge on there. So yeah, we might have to do something about that. That one isn't bulgy, but that's got a bulge on it. So here's one of our smoothing capacitors, so maybe that's seen better days. Got a little bit of, I was going to say got a little bit of rust on the transformer, but I was wrong, it isn't rust. I think that's just where it's been lacquered or conformally coated. Yeah, but I said we've got a bit of a hybrid affair, because I can actually see down there we've got well, some form of transistor. I'm guessing it may be a voltage regulator, something like that, because I'm guessing where we're looking at the moment inside here, this is the power supply. Of course, we've got some of the dreaded Hunt's capacitors. I'm not sure, these blue ones, Phillips capacitors maybe. So it looks like we've probably got some recapacitizing to do, so we'll have to do that. So it looks like this is maybe the main oscillator section. Again, no service information, so I'm not exactly sure. Everything seems really quite nicely screened. Of course, we've got quite a number of valves in here. We don't know what they are yet. Some of these valves have got screening cans fitted to them. So I can see we've got a couple of quite large capacitors, and again, these are the type that are multi-element. So I can see that this one says yellow, 16 microfarad, and it's got green, which is also 16 microfarad. And then this one I think again says the same, yellow and green. So I'm guessing that probably what we've got here is, as I say, we've got two audio frequency generators in here, two audio frequency oscillators. So I'm maybe guessing that these are just paired up. So there's like a left oscillator and a right channel oscillator. So what these actually do is it will produce two separate AF tones, and then it actually mixes them together. So I've just turned the unit upside down, and I think we'll have a go at taking the bottom cover off, because I think that will expose a little bit more. Now, just looking at the old girl, this isn't her first date at the prom, because I can see she's got some screws missing out of her bottom. Well, I was just pondering what looks like quite a big connector here, and I also saw that we've got this long shaft, and well, of course, being nosy, I had to give it a bit of a turn, so let's do that. So it looks like the entire front of this maybe pulls out, he said. So just taking a look inside at the power supply section, it's got those lovely kind of curved, very much like organic traces. I always think that they are almost like pieces of art in themselves. I do think they are, you know, much more interesting and nicer than, you know, all the 45 degrees and square angles. So these were obviously weren't done by any kind of electronics CAD. Back in the day, somebody drew all this on a drawing board. So I can see a couple of capacitors here. There's one there. Yeah, it's a capacitor. But I can see this capacitor here. It's got the vent ruptured on it, so that's going to need some work doing on it. I can see the little rupture mark. So if I just take my poking stick, can you see there? It's got a little split in the capacitor, and this is where it would have had a vent internally, and the capacitor's ruptured, and yeah, it's let the SMU out. Now, interestingly enough, this has a bulge in it, but I think it's the one over here, the one that doesn't have the bulge in it. I think that's actually the one that's I think that's the one that's vented. Let me just double check that. Yeah, okay. So it's the other capacitor that's vented. So this blue coloured capacitor here, this is the one that appears to have ruptured, and I think this is just a single capacitor in a can. I'm struggling to get the angle to read it. I think it's telling me that it's I think it's saying it's 40 volts at maybe 50 microfarad. So it's an enormous capacitor for well, an enormous capacitor for quite a low value of capacitance. Okay, we've got an ECL82 here, another valve made in Great Britain. Got to admit, I wasn't expecting that. I was expecting this to be some form of rectifier valve. An ECL82 is actually an output pentode valve. Now, it's maybe not unusual to see output pentode valves to be used in high voltage regulation stages, so I'm guessing what this is. This has probably got some form of high voltage regulator, because you wouldn't want the frequency of your oscillators to be drifting around. So I'm guessing rather than maybe just feeding, I don't know, 150 volts HT, whether if it was just feeding it directly off a diode and a smoothing capacitor, if your mains voltage varies slightly, or when things warm up, you would get your voltage and your oscillators would slightly change frequency. So I'm guessing that they're using this ECL82 valve as some form of voltage regulator. Now, there's also some adjustment point down there, so maybe that would confirm that. Not exactly sure. Again, no service data, so we are guessing. So down right at the bottom here of this, really what is quite an enormous heat sink, I can see that we've got what looks like a power output transistor. So I'm guessing that this is a series pass transistor. It's maybe predates voltage regulators. I can't actually read the writing on it. It's kind of too far down, my eyes aren't that good. But it's also got a couple of transistors next to it, and maybe that is down there is a Zener. So I'm guessing what we might have here is some kind of discrete regulator circuit. So this capacitor is 1200 microfarads at 40 volts. Well, the nearest that I got to that is 1000 microfarads at 63 volts. So that's what's going to go in it for now. That'll probably be fine. I might actually go up in capacitance value. I might put a 2000 in, but I don't have one, but we might put a 2000 in when we put it back. But just for testing purposes today, I think this is what we're going to go for. Okay, so that'll do for our testing purposes. Now, I want to take a look at these bridge rectifiers, because I think they're bridge rectifiers, because I thought I saw some cracks in them, which would be bad. Okay, so it is a rectifier and it does seem to be measuring good. Let's just check the other one. Okay, so it looks like the bridge rectifiers are okay. So I've just spotted our bulb holder here, and it's actually got a piece of wire soldered direct to the bit of the bulb, so I think we've got some shenanigans going on here, and I can also see that we've got a modern plastic cable tie, so that's not original. So it looks like some work has been done in here previously. Well, I'm rubbish at reading date codes. I don't know, C431BR, I guess that isn't a date code, is it? 1250G, that's the capacitance. 22206, could that be 60? I don't know. So just taking a quick look in the main unit here, I can see that we've got some what I would call fairly modern RS capacitors. So somebody's actually done some work in here, so they're new, modern replacements. We've also got quite a number of these mustard pot style capacitors. Now these are generally quite reliable. We've also got some plastic Hunts in the back. Everybody gives the bad names to Hunt's capacitors in my opinion. They're really no worse than the other capacitor. They're probably just old and probably need changing out. So in theory we've got two oscillator stages here, and they should actually be complete mirror images of each other. They should be symmetrical. So hopefully if we've got a fault even on one side of the oscillator stage, we can actually look at the other oscillator to try and figure out what's going on. So based on having a quick look at that, I'm hoping we don't have to do too much work on this. It may just come together because somebody's obviously been in here. And I think whoever did the previous work, you know, I'm not seeing burnt wires or any of that kind of thing. I think whoever repaired this previously has done the work to quite a high standard. There's, you know, I'm not seeing any obvious bodgery. The only bodgery I have seen is that that light bulb up there, but yeah, sometimes needs mustn't there? So yeah, maybe that's okay. Well, I think what we'll do next is I'm just going to check the fuse, and then I'm going to go and have a brew, because it's definitely brew time. Is the fuse intact? I think it is. I can see a ginger one in there. Now unfortunately my poor old eyes can't actually read the current rating on there. I can see it's written there, but I can't make it out. So well, it's quite a fine wire. I'm sure that will be fine. Yes. Well, I've actually gone ahead and I've replaced all the electrolytics in here. I was in two minds because they've actually tested okay. None of them have tested particularly badly. But my thoughts on the electrolytics is, you know, they do have a definite life, and that life is typically around 10 years. And they've tested good, but because this is a piece of equipment I intend to keep and use, you know, as my own piece of equipment, I would rather not have the worry of one of these capacitors failing. So while we're in here, it's just easier to replace some of the capacitors now. So yeah, cut a long story short, that's exactly what I'm doing. I'm replacing them now. So this is the Plessy capacitor that I decided to remove, and oh yeah, we have got a date on this one. So this is May 1967. So what's that? That's 50 years old, and it's a 450 volt rated capacitor. So I actually think that, yeah, it deserves a rest. So first of all, just going to measure between live and neutral of our plug. We get 22 ohms, so that's typically, that could be in the ballpark for a transformer. Could be a lot higher, could be a lot lower, but it's not 0 ohms. Just check the switch, and it goes to infinity, so the switch is working. We want to make sure the switch is on for what we're doing, so we switch on and we see our 22 ohms again. So the next quick test I'm going to do is earth continuity. Now this really should be done at high current, but as a quick test this is better than nothing. So I'm going to go to the earth pin and the chassis of my piece of equipment, and it's coming up as 0.4 ohms, and probably most of that is in my test leads. 0.3 ohms. So that goes to prove at the moment we've got an earth connection between the earth pin on here and the chassis of our piece of equipment. And I did go away previously, I took the cover off the plug and I just made sure everything was in good order, and it did have a 3 amp fuse in it, so that's good. So the next test that I'm going to do is an insulation resistance test. So the way we do that, we take our plug and you need to link both the live and the neutral conductor. You need to link them together, as I'm going to do with this strap. You need to put one of the connections on the chassis of the equipment, and the other connection we're going to put on these live and neutrals that we've just linked together. Okay, we've got that. I'm going to set this, because this piece of equipment operates at 230 volts, it's typical to do an insulation resistance test at twice the working voltage. So for this meter we could do it at 250, but we're actually going to do it at 500 volts because that's twice the working voltage. So the first thing I'm going to do, having powered up my tester, I'm going to make it fail to make sure the meter's working. So we touch that and the meter drops to 0, so now I'll go on here. Okay, so our meter here, that's gone up to infinity, so it means that we've got better than 200 megohms of insulation between our earth and our live conductor. So we turn it off, switch that off, and that is good. Basically, you want the higher the reading, the better. I wouldn't really worry too much. If you get anything much less than 100 megohms, I would be investigating why. If I had anything below 10 megohms, I certainly wouldn't be plugging it in. Now, because I'm running this up for the first time and I don't know much about this piece of equipment, I'm going to be running it up using both the variac and the lamp limiter, which is somewhat belt and braces, but then again, why not? So in the bottom section of our chassis here, we do have quite a mixture of old and new electrolytics. So that's a newish one, that's a newish one. The mustard caps aren't electrolytics, they're normally pretty reliable, these are mullards. But we have actually got some high voltage smoothing capacitors here and here. So those are ones which I am going to be looking at them quite carefully, and because we've got these old electrolytics and I haven't changed them out, I'm going to be taking a look at the voltages on them, because I think in theory, because both halves of this two-tone generator should be symmetrical, whatever voltages we see on one side of this capacitor, we should see similar ones on the opposite side of it. So I'm just going to be poking round. Now I'm obviously going to also turn the power up a little bit more gradually, because to give these things a chance to wake up. Well, as you can see, we've gone ahead and we've powered it up on the bench, and it does appear to be working to a fashion. Now I say that it may actually be fully working, but I've got to admit I am having some problems with it, and it could just be that I don't understand how to operate this piece of equipment properly, because I haven't got any service data for it and I haven't got a manual, so really we're going blind. I have operated them in the past, and all the ones that I've operated, particularly the Marconi one, they work a little bit differently to this. But what we've basically got is we've got two signal generators, and they call those signal generators A and B. So on the left hand side, on this side we've got the A signal generator, on the right hand side of the instrument we've got the B signal generator. So at the moment it's actually set to produce an output from the A signal generator, because we have a big paddle switch here, so that's set to A. What we can also do is we can flick the switch to the B position. Now it would actually be outputting a signal from the B signal generator, but the most important thing that this actual signal generator does, it actually mixes the A and the B signals together. So you've got a center position here that's called A plus B. So when you actually use this instrument, you actually use it in the A plus B mode, and what that will actually do is that will produce kind of a modulated output, and you can feed that into the microphone socket of an SSB transceiver, and you can use it to align the SSB section. So taking a look at the A section first, I'm going to flick the switch to A. You can actually see here we've actually got some frequency controls. So we've got a times 10, a times 100, a times 1000, and then we've got a fine frequency control here. So at the moment I've got this set to times 100 and it's set to 10. So 10 times 100 is 1 kilohertz. And we've also got the signal being fed out of here. I've just got this going into my little signal tray, so I'll just turn the sound up. So you can hear that, can't you? So we're getting an audible tone there, and I can vary its frequency. So sorry for any dogs that may be watching, that could have been quite distressing. Now on this side of the instrument you can see we've got a large output meter, and that just reflects the signal output level. So again we're switched away at the moment, so you can see we can turn the output level down, or we can turn it up. I'll just turn it down. Let me just turn the audio up a bit so you can hear it. So we can turn that up, or we can turn it down. And it's quite a nice scale that this instrument's got on it, and that it's got a mirror behind it, so you can eliminate the parallax error, and it does actually appear to be very accurate. So at the moment we've got this set to 1 kHz again. Let's have a look at the output on the scope. Now I've had the instrument switched on for about half an hour to warm up, and it's set to 1 kHz, and it's actually displaying 1.004 kHz at the moment. So for an analog instrument, which this is, you really couldn't get a better frequency output than that, could you? It's absolutely bang on. So let me just expand the time base a little bit, and that looks like a fairly high purity sine wave to me. Certainly you really can't tell by eye unless the sine wave is massively distorted, but I'm going to call that good because I've got no reason to believe it's not good. So on the left hand side of the instrument you saw that I was adjusting this level control, and this is a fine level control, so I'm going to set that pretty much bang on 2, which is where it was before. But we've also got a coarse level control. So this coarse level control, this actually works on the A and B channels together. So at the moment I've actually got it set it to the maximum output, which is 30 millivolts, but we could actually turn it up, or we could turn it down again. And I've just noticed it's even got an off setting, so you can turn the output completely off. I'm going to set it to the 30 millivolt output, which is where we had it before. And because we're on the 30 millivolt output, we're on the free scale here, we're on the lower scale, and it's on 2, so this output would correspond to 20 millivolts. Now this instrument does actually have 2 sets of outputs. One of them is 600 ohms, which is the one that you would actually inject into the microphone of your transceiver. So that's kind of 600 ohm, that's kind of an audio standard. Now this side here, this side here is a high level output, which I don't think it goes through the attenuator, so this is what I'm feeding into the oscilloscope. So at the moment these levels that we're setting on the meter, they don't necessarily correspond to the output levels, but I've actually also had the scope connected to the other connector here, the 600 ohm one, which is correctly attenuated, and those do match the meter readings precisely. So these levels are actually in RMS. So that was just a quick run through of the A-tone side of the signal generator. Now there is also a B-tone side here, and it's the B-tone that I'm having problems with. So I'm just going to flick that over now. And you may think, well, there's no output from it, I can't hear anything. Well, you'd be quite right, you can't actually hear anything, but I promise you there is an output. And the level meter here, again, it's telling the truth. We have got a 20 millivolt output, just the same level of output as we had when we had in A. So the question is, why can't we hear anything? Well, let me show you. So I've switched it back onto A at the moment. Now I'm just going to flick the switch. I'm actually going to switch it to the AB position, and to be honest, that's what I would expect us to see. We are kind of seeing a modulated waveform there, so we're seeing the A and the B waveforms being mixed together. But now I'm going to continue flicking the switch to its B position. And the problem, or what I think is a problem, is we've got precisely the correct output level. We have got a lovely high purity sine wave, so there's absolutely nothing wrong with that. He said, fumbling for the time-based control. Don't use the scope enough, do I? So yeah, we've got a sine wave there. It does look like a sine wave. It doesn't look distorted to me. But the problem is the frequency here. It's only 72 Hertz. Now I would have thought that it should be much higher than that. I mean, typically you might use frequencies of, I don't know, I'm going to make it up, 600 and 2.3 kilohertz, something like that. So I actually think that this frequency here is too low, and I think that at such a low frequency, well, I'm kind of guessing that that might have trouble getting through the capacitor stage of a microphone, of an SSB transmitter. That's just a very low audio tone. In fact, I can't, you can't hear it. So this is actually producing just the same level, but I can't hear it on the on my signal tracer. Well, okay, you got me there. I did mislead you slightly. I can hear it on the output from my signal tracer, but because human hearing isn't necessarily that sensitive at the low frequency, it doesn't sound anywhere near as loud as the 1 kHz tone does. So I've actually turned it pretty much full up now, my signal tracer, and hopefully you can hear that in the background. But if I just compare that to the actual output from the A side of the tone generator, you see the levels are the same, but they sound totally different, which is quite interesting in itself. Now the frequency control for the B side of our tone generator, it's quite different to the A side, which is very, very adjustable. This one just consists of a number of steps. They seem very, very low to me. I just think that we would have been expecting a much higher frequency range, maybe something similar to the A side, but as I say, I don't have a manual, so I'm not exactly sure. So I've got our tone generator set to the minimum level at the moment, and you can probably see there, hopefully you can see on the oscilloscope, the output is 72 Hz. So I go to B, and now it's jumped up to 79, now it's jumped up to 91, 103, 111, 116 and 127. So you can see that our frequency control does go up in approximately 10 Hz steps. So that may be right, this may be how it's actually designed to operate, but I just don't trust it. I think that should be a higher frequency. So because I don't trust it, I think what we'll do is we're just going to do some cross measurements between the A side of the timing components and the B side, and just have a look if we can find anything obvious. So we're looking down into the top of our signal generators here, and I'm guessing that these sections, this section here does the timing for the frequency of the A side, and this board over here does the timing for the B side. And I'm not implying any special super electronics knowledge here. All I'm doing is I'm tracing the wires from this timing control here. I'm tracing that, and also these wires, and these obviously go to these banks of capacitors, and they will pull these capacitors in different sequences to actually get the frequency ranges. So if we just turn it around and have a look at this side, we can actually see that there is at least two of the capacitors look very similar to these on the other side. So what I think that I will do is we'll actually see if we can take a look at them capacitors, see if they're actually of the correct value, because I don't know, I'm guessing that could be where my problem is. I'm not sure, but it's worth a try, isn't it? Okay, so what have we got here? We've got two that say 100k, so we've got two 100k's at 63 volts, but interestingly enough, these are 1% capacitors, and in fact everything in this what I'm going to call the timing chain, that's going to be confusing. Have a look at the timing chain. Today we're repairing bikes. Now, these are the timing components, I'm fairly sure that they are, and the fact that they've used 1% capacitors kind of, yeah, that's what they're doing. They don't want these things drifting everywhere. So these, it says 10k and 10k. Certainly the two big ones say 10k on them. So I'm going to go ahead and measure them, because I'm hoping that we've got the same capacitors on the other side. So 10k, I think that's going to be 100 nanofarad, isn't it? Sorry, not 10k, 100k. 100k is going to be 100 nanofarads. Okay, and that amazingly enough comes up bang on, spot on, 100.7 nanofarads. So that looks good, doesn't it? We're happy with that. Let's check its friend next to it. Oh, that comes up as 4.8 nanofarads. Well, I'm not going to just give up at this stage, because it could be this range selection switch. Okay, so I've just turned the switch here, and now that's come up as 103. So we're just bringing in different capacitors here depending on which, whether it's set to times 10, 100 or whatever. So yeah, so the basic capacitance of both these big capacitors, they're 100 nanofarad. So what I'm going to do is I'm just going to repeat that exercise on the opposite side and see if it yields, well, see if we get the same answer, if we get something different. Now unfortunately there's various gizmos and switches and God knows what's in the way, so yeah, not very easy to get at. I suppose I could just unbolt that switch, that would probably come off fairly easily, but I'd probably rather make it hard for myself. Let's see if we can just poke something in there. Okay, so we're on the top capacitor there and that's just come up open, so that could actually indicate something, couldn't it? I'll just try the selector switch. Well, I was going to say this capacitor comes up open all the time, but it's actually calling me a liar. Is there something loose in here? So the bottom one just says it's open all the time, so I'm sure you'll agree that just looks a bit suspect, doesn't it? So I think that certainly it bears a little more investigation. I can't be sure that that's what it is, but I think we've got to have another look, haven't we? Well, it's a little bit hard to tell, but there does seem to be something in here that's responding to pressure around that capacitor. Now, it's reading 102 nanofarad now, it's reading perfectly, and the reality is I can't actually make it fault, but it has been faulting a lot, and but now it seems to have, well, see, it went open then. Did you see that? I didn't imagine it, did I? Now we've actually got the wires soldered on now, so that should be a good connection. Well, I don't think it does say open. I don't know if you can see that. This seems to be staying rock solid. Oh, it did it again. That went to open then. So is it this meter that occasionally calibrates and goes to open? Well, I have actually spent quite a lot of time off camera digging into these two capacitors here, and you can see at the moment I've actually even soldered in an additional 100 nanofarad capacitor. Had a look at what effect that has on the circuit, and yes, it does drop the frequency slightly of the section B. So having spent a lot of time messing with these capacitors, I am quite happy that they are good and they are in circuit as they should be. I've also spent quite a lot of time looking at all of these precision resistors here, these blue ones which are 1% resistors. They appear good, and there's also a number of very high precision resistors on the underside of the chassis here, which we've also taken a good look at, again off camera, and I think I've really come to the conclusion, having slept on it, that this signal generator is actually working as it's designed to work. The reason, of course, I don't know is because I've got no information at all on this signal generator. You see, we've got tone A, which is working at a relatively high frequency from 10 to 30 kilohertz, that's fine. The actual B frequency here is only going up to about 120 kilohertz. Well, this instrument is designed to actually feed in an audio signal into the front end of your transceiver via the microphone connection. So I think that a signal at 120 Hz, which is the maximum that B goes up to, I think that's likely to be out of the audio passband, and there's not a lot of point in feeding a signal in, a tone B, which your transceiver won't be able to see because it's effectively going to be filtered out by the front end coupling capacitors. That's why I think there's something wrong with it, why I was expecting this. Typically the frequency for B would perhaps be between 400 and 600 Hz. That's typically what you would have. It wouldn't be 120 Hz. But I've done a lot of poking around with this circuit, and I've also slept on it since then. I guess really quite an obvious thing which I should have thought of earlier is that when we look at the A range, we've got settings from 10 to 1000 Hertz, and you can see that we've got this bank of capacitors here. Now this bank of capacitors is actually wired to this selector switch, so it does actually pull in different banks of capacitors. It actually pulls them in from, well, I can't see some of the values, but it looks as though it pulls them in from about 1 nanofarad, then the next one is 10 nanofarad, and then there's a couple of banks of 100 nanofarads, and then, well, there's a couple of others at the end as well. But basically what I'm saying is it does actually pull these capacitors in different ranges, and I'm guessing that that coincides with 10 100 and 1000, and I'm guessing that when it's on the 1000 range it probably pulls in this very small capacitor here. But if we look at the other end, we don't actually have any small capacitors in circuit, we just have the two big 100 nanofarads. Well, I'm guessing that I can just quite crudely test that assumption by seeing which ranges these capacitors come in. So we're at the times 10 range now, so yep, that's not in circuit, that's not in circuit. Yep, the first of the big capacitors in circuit, the second of the big capacitors in circuit. Not in circuit, not in circuit. So let's go to 100. Not in circuit, not in circuit. Okay, that one is in circuit, so that obviously works on the 100 times 100 range. Let's put it on the times 1000. So the very small capacitor is in circuit when we're on the 1000 range. Not in circuit, not in circuit, not in circuit. Well, of course that's perfectly obvious, isn't it, for an oscillator. I'm guessing that when this is set to the 10 range, it brings in these two big capacitors here. Those are the two that it brings in, which would probably coincide with, they are the same size as these two capacitors here. Again, I think that the B range is designed to work at a much lower frequency of the A range. Now, I do think it is quite strange that this frequency B control doesn't actually have any markings on. You'd think they'd have given us a clue at what actual frequency they was designed to operate on, because it just says from A to G. And of course they haven't done that. So I also wonder if maybe these, maybe some of these values here that populate the B side, were they almost like factory fitted depending on the usage of this two-tone generator. Maybe there is some applications for two-tone generators that need to have a very, very low frequency B. Maybe that's the case, and that could just be an application that I'm personally not familiar with. So I've been trying to decide what to do with this. So I think the first thing to do is we're going to try it, and then maybe what we'll do is, if we have no luck trying to get 120 Hz into the transceiver, what we may just do is we may just change these two big capacitors here for something smaller and see if we can actually set up a frequency of 600 Hz then somewhere on here. Because what we could then do is we can use the B side to produce a lower frequency of 600 Hz, and then we can use the A side to produce like the high frequency 3750, something like that. When you're looking at a piece of equipment like this, you never quite know how it goes, so we just switch the camera on and what happens happens. So this maybe hasn't been a particularly exciting episode, but well, such is life. Until next time, as always, thanks very much for watching, but for today that'll do. Bye bye for now.